Okay, Assalamualaikum and good day everyone. So now we have a new topic for this mechanical system. Previously we have learned about the translational of the mechanical system, and now let's move to the modeling of the mechanical system. So now we want to focus on the rotational system. Okay. Similarly, if we compare to the previous translational system, we have three components. We have spring, viscous damper, and mass. That is, for the spring we have K, or for the viscous damper we have Fv, and for the mass we have M. And for the rotational system, we have a similar component. We have spring, we have viscous damper, and we have inertia. But now let's just change the representation of the viscous damper and inertia. Viscous damper we use D. For the inertia we use J, and we replace a force with a torque. And then for this rotational, we replace the mass with a inertia. Okay, so we have for this system, let's focus on the torque angular displacement here. Okay, so for the torque, for the spring we have K theta T, and then for the viscous damper we have D theta dot. We can also represent with a theta dot here, and then for the inertia we have J theta double dot over here. Okay. All right. The way we find the equation for this rotational system is in similar fashion that we have learned to find it in a translational system, where the steps is we can replicate the step that we find the translational system, but in this case we want to find the rotational system. So for example, in this case we have two inertia, J1 and J2 over here. So this is actually 2 degrees of freedom. So we have two equations for this rotational system here. What we want to find is we want to find the so this is the output theta 2, and then this is the input torque here. So we want to find theta 2t over t. Okay, we want to find the transfer function of this rotational system. So what we need to do is the first step is we find the torques on J1 due only to motion of J1, and then the second one we find torques on J1 due only to motion of J2. Okay, and then we combine all the torques in equation in the step 1 and step 2. And then next we proceed with the step 4, where we find the torques on J2 only due to motion of J2, and then we find torques on J2 due only to motion of J1, and then we combine all the torques that we found in step 4 and step 5. And finally, before we solve for the transfer function theta 2 over t, we write the equation of motion that we found in step 3 and step 6. So let's demonstrate this example here. Okay, now we have two inertia here. We have J1 and we have J2. Okay, for J1, let's focus on these blocks here. Okay, for the J1, we have torque. Okay, so the theta 1 here is in torque direction. Okay, we have torque and we have theta 1 direction over here. And then what we need to consider for the inertia J1 is that we need to consider the inertia of J1 itself, inertia of J1 itself, and then we need to consider the viscous damper D1, and we need to consider the spring K. Okay, and for the step 2 is we find torques on J1 due only to motion of J2. So we need to see, in this case, J2 is connected to the spring K. So we have to consider as well the direction of theta 2 due to motion of J2. Okay. So we combine step 1 and step 2 here, so we can come up with a diagram of 3 here, and then the diagram of 3 we can use this diagram to write the equation of motion of the inertia J1. So theta 1, okay, theta 1 is a combination of a summation of inertia J1, and we have a viscous damper D1, and then we have the spring K in the theta 1 direction, and then we also need to consider the K in theta 2 direction over here. So the summation of all this is actually equals to the torque given to J1. Okay, so now we have find the first equation of J1. All right. Next, we proceed to the next inertia. So we have J2 over here. So we need to consider J2. Okay, so J2, there is no torque applied on J2. So we only have J2, we have the viscous damper D2, and finally we have the spring in theta 2 direction K. And then we need to consider as well the motion due to J1. So J1 is connected to the spring K, so we have K in theta 1 direction. So we can come up with the second equation where we have, there is no torque, so that's why we have equals to 0 over here. And then we have for the in theta 1 direction, we only have due to spring that connected to J1, that's why we have negative K over here. And then in theta 2 direction, it is contributed by the J1. We have the viscous damper D2, and we have the spring in theta 2 direction K. So we already have two equations of motion over here. So these two equations of motion, we can use it to find the transfer function theta 2 S over Ts. So next we can, before that we can summarize that the steps to find the rotational, the equation of motion for the rotational system is similarly to the steps that we can use to find the translational equation of motion for the translational system, where we have the sum of impedances that connected to motion at theta 1. So we have theta 1 minus sum of impedances between theta 1 and theta 2. Theta 2 equals to the sum of applied torques at theta 1. Okay, and then we can use the same concept to find the equation of motion for the J2. Okay. All right. Now we have another example here. We have the rotational drive system. All right. Now we have 2 degrees of freedom as well. So we have 2 degrees of freedom. So because we have J1 and we have J2. In this case, there is no torque mentioned, no torques given in this system. So we can say that we have to find the 2 equations. So this is the first one. So we consider on the J1 first. Okay, J1 first. So J1. All right. So for the J1, so we have to consider the J1 itself. So we have J1. So we have theta, because it is rotated in the direction of theta 2 over here. So we have theta 2. Okay, we have theta 2. double dot J1 theta 2, and then we have viscous damper that is connected to J1, so we have C. So we have C, we have theta 2 dot, and then we have next one, we have spring. We have spring, so we have plus, we have a K. Okay, so we have K in theta 2 direction. Okay, and then next one we need to consider as well the motion that is caused by theta 1 and theta 3. Okay, theta 1 and theta 3. So in this case, we need to subtract from the spring due to theta 1 over here. So we have to minus K theta 1, and then we also need to subtract from the viscous damper that is connected to J2, which we have minus, we have C and theta 3 dot over here, so equals to 0 because there is no torque that is applied on this system. Okay, next one we find the equation of motion of the J2. So in J2 here, the first one we have J2. Of course, we have theta 3 double dot because of this direction, theta 3. And then that's it for theta 3. Now we need to consider the motion that caused by J1 because it is connected to damper and connected to J2. So we need to minus, we have over here is C. We have C theta. Oh, sorry, we need to consider the damper for theta 3 first. So theta 3, okay, and then we need to minus C theta 2 dot equals to 0. Okay, so this is the first equation of motion, and then this is the second equation of motion. So now we can proceed to find, because this is the output is theta 3 and the input is actually here is theta 1. So we want to find theta 3 over theta 1. Okay. Remember last time when we have the parameter, we list out what we want to find, what is the input, what's the output. So basically theta 3 is the output, so theta 1 is the input, and then we have other parameter which is theta 2. So we no need to find the equation for theta 1, so we only need to consider theta 3 and theta 2. We find the equation so that we can use the equation to draw the signal flow graph. So that's why we convert this equation of motion of 1 and 2 to this new equation, equation 3 and equation 4 over here. We transform it to the Laplace domain. We transfer it to the Laplace domain. So theta 3 is double dot here. So we can draw the signal flow graph. Signal flow graph. So we have here theta 1, we have theta 2 and theta 3. So the input is always at the first node is the input, the final node is the output, and in between we have other nodes that we define in the equation. So in this case we have theta 1, theta 2 and theta 3. So we already have the equation for theta 3 and theta 2, so we can draw the signal flow graph. So for the theta 3, theta 3 is connected by theta 2 and theta 1. So theta 3 is connected to by theta 2 as well as theta 1. And then we just write down the system, the system of theta 2 to theta 3, and then to theta 1 to theta 3. And then next one we have the from this equation we have theta 2, which is contributed by theta 3, theta 2 which is contributed by theta 3. So we write down the equation as well. So finally, when we have this signal flow graph, then we can apply the Mason gain formula to find the output of theta 3 over theta 1 over here. So T1 is actually T1 is actually this one. So this is T1, and then for this theta 3 over 1, we need to find delta, where we have our delta is equals to 1 minus this loop over here. Okay, so that's why we can have theta 1 delta 1 over delta, where our delta 1 is equals to 1 because there is no loop that do not touch the T1. So we can put into this equation Mason gain formula here, where we have theta 1 delta 1, where delta 1 is actually 1, so we have T1 over delta. So this is actually the simplified version of this simplified fraction that we found using the Mason gain formula. And if we want to find other transfer function, let's say we want to find the theta 2 over theta 1 here, so we can use the same signal flow graph over here to find this transfer function. Okay, to find this transfer function is actually we need to find the first T1, T1, which is actually the output is this is the output. Okay, this is the output. So this is the output. This is the input. So we need to find the T1, which is the forward path from the input to the output, which in this case here and here. Okay, so we have T1 is equals to this. Okay, this multiply by this. Alright, and then we have delta 1 as the same. Delta 1 is actually equals to 1, and delta also similar in this first example here. So our delta is 1 minus loop over here. So this is the loop here. So this is the delta 1 minus this loop, and then we can find the transfer function theta 2 over T1 in what we call it similar steps that we have found our theta 3 over theta 1 just now. And this is the we have J1, J2 and J3, so you can guess what type how many DOF of this system. So basically it's 3 degrees of freedoms because it have 3 initial J1, J2 and J3. So you can write the equation of motions where we have 3 equation of motion, J1, J2 and J3. So you can use these steps to find the equation of motion of the J1, and then you can find J2 equation of motion using these steps, and finally you can find the equation of motion for J3 using these steps, and finally you will get this as the equation of motion. So I need to I need you to try to do this exercise and then see whether you can get these three equation of motion over here. So try to practice because again it is important for you to try all the exercises that has been shown in this lecture slides, because I want you to get the feel of solving the problem without looking at the final answer. Okay. Alright, so this is the end of this video. Next video, I will explain to you the mechanical system where we have gears. Alright, so until then, thank you very much. Assalamualaikum and goodbye.